Okay, so 11.3, we're only going through the first part. The first part of 11.3 is all that's on the quiz. So a reminder, because of Aspire testing happening starting Tuesday, we are reviewing tomorrow for the summative quiz, everything we've had in Chapter 11 so far, 11.1 through 11.3a. And then quiz will be on Monday so that we're not having a quiz on the day we have Aspire testing. But this is being able to construct a probability distribution, and we are only going to be doing this for theoretical probabilities. And part of it is first looking at how to define a random variable. Is the random variable discrete or continuous? So more terminology you need to understand and be able to identify. And then we'll actually get into a probability distribution for a random variable x. So what I have at the top is just information so you understand the difference between discrete versus continuous and then what the distributions look like. So it says, first of all, a sample space. When dealing with probability, a sample space is the set of all possible outcomes in a distribution. So it says, consider a distribution of values represented by the sum of the values on two dice, and it gives a distribution here of that. And then also a distribution of miles per gallon for a sample of cars. So it gives another distribution. These you can see there's similarities. There's also differences in the sense that this is given as a bar graph. This is more continuous. So do you have a question, Adler? Okay. So then it says below the sum of the values on two dice. So if you have two regular six-sided dice, and you took the sum of the values on the dice, the lowest sum would be if you had a 1 and a 1, so the lowest sum would be 2. The highest sum would be if you had a 6 and a 6, so 12. Or you could have any number in between, I should say any whole number in between. So the sample space would be the numbers 2, 3, 4, 5, 6, all the way up through 12. This distribution is discrete because the number of possible values in the sample space can be counted. There's a limited number of values in the sample space. It's only the whole numbers between 2 and 12. However, the distribution of miles per gallon is considered to be continuous because it says while the sample space includes any positive values less than a certain maximum, so it's talking about miles per gallon, that would be a positive, they would all be positive numbers. It's coming up with saying a maximum could be around 100. So even though there would be that maximum, they would all be positive. The data could take on an infinite number of values within this range. Kind of the difference between discrete and continuous, I'll put it in terms of this. Sums of two dice, you'd be dealing with whole numbers. You can't roll a sum, for example, of 7.5 or 10 and 1/3. But with miles per gallon, you could have 25.5 miles per gallon. You could have 18.9 miles per gallon. So there's infinitely many values here, whereas here you're limited to specific values. So then more definitions before we get into these first two examples. It says the value of a random variable is the numerical outcome of a random event. A random variable can be discrete or continuous. Discrete random variables would be countable values like the sum of two dice. Continuous random variables can take on any value within a given range. So again, think of, are there specific values I could have, or could the value be anywhere in between a certain range, including any decimals or fractions, is kind of what you're looking at between the two. So in example 1, this is just getting you to identify in the situation what is the random variable and then classify it as discrete or continuous and explain why it's discrete or continuous. And I just have two examples here for us to write down. So if we look at A, it says the number of hits for the players of a baseball team. So first of all, when it says identify the random variable is basically what's being described here. So I'm going to just say the random variable would be the number of hits. It would be what you're measuring. So I'm going to write this in a complete sentence here. The random variable is the number of hits and then knowing what I just described above, would you say the number of hits for the players of a baseball team, would that be a discrete random variable or continuous? I heard somebody say discrete, and why would you say discrete? Yes, so the number of hits would all have to be whole numbers. You're not going to have 2.5 hits, anything like that. So the random variable is the number of hits, which is discrete because, I'll just say because it is countable. You could count the number of hits each player has, and you're not saying, you know, they could have 2.5 hits or 1 3/4 of a hit. It would either be 1 hit, 2 hits, 3 hits, and so on. Okay, and then we have for part B, the distances traveled by the tee shots in a golf tournament. So what is it that's being measured in this situation? Distance. So the random variable is distance. And then would you say the distances traveled by the tee shots, would those be, or would that be a discrete random variable or continuous? And why would you say continuous? Yeah, so this you could include, it's not like it has to be a whole number of feet or a whole number of yards. You could have those in-between values, those decimals or those fractions, those partial distances as well. So the random variable is distance, which is continuous. Because I'll say it can take on an infinite number of values. And this is just one way to describe it. So, like I said, again, describing it in some way to say, you know, that you can have those partial distances. It's not just specific distances that would be counted. The distance really could be anything within a certain range. So any questions right now on identifying a random variable and identifying it as being discrete or continuous, that difference between discrete and continuous? Okay, so then the probability distributions that we're looking at, we are just going to be looking at discrete probability distributions in terms of making them. So looking at random variables that have sample spaces that can be counted. So a probability distribution for a particular random variable is a function that maps the sample space to the probabilities of outcomes in the sample space. So you're looking at each outcome in a sample space and saying what the probability of that outcome is. Probability distributions can be represented by tables, equations, or graphs. So we are actually going to be representing them by tables. We'll be making a table as well as drawing a graph of it. So we'll be making a bar graph. And like I said already, we're focusing on discrete probability distributions where you do have a fixed number of outcomes. And I just have some additional information below dealing with not only probability distributions, but probability in general. So a probability distribution can be determined theoretically or experimentally. And I do want to explain this difference. We are just doing an example of a theoretical probability distribution. Theoretical would be based on what you would assume to happen. So theoretical is based on assumptions. Thinking of it this way, say you have like a fair die, a fair six-sided die, you would expect your chances of getting any of those six sides would all be the same. That would be the theoretical probability, is that each side has a 1/6 chance of turning up when you roll a dice. Or same with like flipping a coin, you have an equal chance of getting heads versus tails. That'd be theoretical. Experimental then is what actually happens. So if you actually flipped a coin 10 times, would you get half heads, half tails? Experimental is what actually happens. So I should say it's really based on experiments, which is why it's called experimentally. If you want to even put more detail than that, based on what actually happens or actually occurs. And that would happen through an experiment. So again, we are looking at theoretical, what you would assume to happen. As it says, we've already talked about it, can be discrete or continuous. We are focusing just on discrete. Probability of each value of x must be at least 0 and not greater than 1. So probability should always be in between 0 and 1. Probability is not negative, and then it's not greater than 1. The sum of all the probabilities for all of the possible values of x must equal 1. So this is just that notation. This is the summation symbol. It means if you take the sum of all of the probabilities of x, the sum of all those probabilities is 1, is what that notation means. So like I said, and I think it's explained at the top of the next page, theoretical probability distribution is based on what's expected to happen. So the example I did give already, distribution for flipping a fair coin, you would expect the probability of getting a head is 0.5. Probability of getting tails would be also 0.5. And if you add those together, it does equal 1. So that's what I was explaining before. So here's the example we're looking at. You may want to, if you want to write this down, I'm going to be using another sheet of paper if you have another sheet of paper to write our sample space out on. If you just want to follow along with what I'm writing and fill in the table that way, that's fine too. But we are looking at our random variable x is representing the sum of two cards drawn from a stack of cards numbered 1 through 8 with replacement. So you draw one card that's numbered 1 through 8, you put it back, and you draw a second card, and then you add the two cards that you got. Okay, so it is possible. The with replacement is important because that means if you draw a 1 and you put it back, you could draw the 1 again. So we are going to be filling in what's called a relative frequency table. And I don't have what all of our 3 rows are representing here. The first row, we need to come up with what our sample space is, and our sample space is going to be all of the sums that we could get. So I'm just going to put sum here. So we're going to be looking for the sample space first, meaning if I do draw 2 cards, what are the possible values that I could get? And we can actually think of it this way. So if you have cards numbered 1 through 8, you're drawing 1, putting it back, drawing a second one. What is the lowest sum you could get? 2. If you drew a 1 and then another 1, what would be the highest sum you could get? 16. If you drew an 8 and then another 8, you could get a 16. And then really, we're going to be actually writing this all out. You could get any number in between that in this case. So we could get a 3, 4, all the way up through 16. Now, this isn't the case for everything where you think of the lowest you could get, the highest you could get, that every number could occur. We will actually see that every number occurs when we work this out. The next row then, once you have your sample space, so these are all of the possible sums you could get by drawing 2 cards numbered 1 through 8. The second row then is going to be the frequency. Frequency is, and again, we're dealing with theoretical, how many possibilities there are of getting each sum. So I'm going to give you this as well, the total number of possibilities. Because we're starting with 8 cards, we're drawing out of 8 cards first and then out of 8 cards for our second card as well. That means the total number of possibilities, just right here, total possibilities, would equal 8 times 8. So there's 64 possibilities. So what the frequency is out of those 64 possibilities, how many times is it possible to get a 2? How many possible times could I get a sum of 9? That's what we're going to be looking for. That's what I'm going to use my extra sheet of paper for. So what I'm going to draw on here is along this row, I'm going to say my first draw. I could draw a 1, 2, 3, 4, 5, 6, 7, or an 8 for my first draw. And then I'm going to do a column for what I could get for my second draw. So this is first. Second draw, I could get the same possibilities. I could draw a 1, 2, 3, 4, 5, 6, 7, or an 8. And I'm just doing this to come up with my possibilities. So let's say the first card I draw is a 1. What I'm going to do is add these together here. So if I drew a 1 and then another 1, I would get a 2. If I drew a 1 and then my second card was a 2, I would have a sum of 3. If I drew a 1 and then a 3, I would have a 4. So notice in this column, they're just all going up by 1s. So here I would have a 5, 6, 7, 8, and a 9. So these are all the possible sums I could get if I drew a 1 first with any other number. Then I would do the same thing if I drew a 2 first. So I could draw a 2 first and then a 1, and I would have a sum of 3. I could draw a 2 and then a 2. That would be a sum of 4. So again, down this column, they're all going to go up by 1s. So then I could have a 5, 6, 7, 8, 9, or I'd be ending with a 2 and an 8, which would give me 10. Okay, next one, if I drew a 3 first, 3 and then a 1 would give me 4. These are all going to go up by 1s. So I could also get a 5, 6, 7, 8, 9, 10, or 3 and an 8 would give me an 11. If I draw a 4 first and then a 1, I'd be starting with a sum of 5. And these are all going to go up by 1. So 6, 7, 8, 9, 10, 11, or 4 and an 8 would give me 12. Fill in the 5 column. First sum would be a 5 and then a 1, which is a 6. So 6, 7, 8, 9, 10, 11, 12, or 5 and 8 would give me 13. For drawing a 6 first, 6 and a 1 is 7. All the way through 6 and an 8 would give me 14. So I know this seems, I'm listing out a lot of numbers. It's not really taking that much time. I would suggest, though, when you have problems like this, you do list these all out. I see students try to just guess the frequencies. Usually the guesses are not correct. Okay, and then my last column would start with 9. And end with an 8 and an 8, which was my largest sum, which was 16. So once you have them listed out, now I'm going to be filling in this frequency part of my table. I'm looking at this list and saying, how many times out of these 64 possibilities could I get a 2? The only time I'm going to get a 2 is if I draw a 1 and a 1. So the only time I get a 2 is once. That frequency is 1. Okay, then I look and see how many times could I get a sum of 3 2 different times. So the frequency of getting a 3 showed up twice in my table. The 4 showed up 1, 2, 3 times. So a frequency of 4 would be 3. 5 showed up 1, 2, 3, 4 times. 6 showed up 1, 2, 3, 4, 5 times. 7, 1, 2, 3, 4, 5, 6 times. 8 showed up 1, 2, 3, 4, 5, 6, 7 times. 9 ends up being the one that showed up the most. 1, 2, 3, 4, 5, 6, 7, 8 times. And then you can kind of see from my table, now the sums are going to start going back down. So 10 is showing up the same number of times 8 showed up. So 10 showed up 7 times, 11 showed up 6 times, 12 showed up 5, 13 showed up 4, 14 showed up 3, 15 showed up twice, 16 was once. Okay, so you're not going to have a ton of these problems, but I would definitely say list out the possibilities. Don't just try to guess how many times something could appear. Then what I would also recommend, because you know there's 64 possibilities, actually make sure your frequencies all add to 64 to know that you found them all. Would be another hint I would give. So any questions on how I came up with those frequencies? Okay, and it's helpful if you can figure out your total possibilities, especially for this next part. This now is going to be the relative frequency, which is also the probability. Relative frequency would be the probability. And probability is always the frequency, or how many times did it occur out of the total number of possibilities. So for the sum of 2, that probability would be a frequency 1 out of 64. So 1/64th is the probability. For a sum of 3, that would be 2 out of 64. And we're going to simplify that fraction. 2 out of 64 is really 1 out of 32. A sum of 4, that frequency or probability is 3 out of 64, which that is already simplified. And then for a sum of 5, that's 4 out of 64, which can be simplified. You can divide 64 by 4, so this is 1/16. For a sum of 6, it's 5 out of 64, and that's already simplified. We can't divide 64 by 5. Sum of 7 is 6 out of 64, which we can't divide 64 by 6, but we can divide both 6 and 64 by 2. So it's 3 out of 32. A sum of 8 would be 7 out of 64, and that's already simplified. And then a sum of 9 is 8 out of 64, which we can divide both by 8. That's 1/8. And then we're going to see those probabilities start to repeat. So we can kind of go off of what we already have here. So a sum of 10 will be 7 out of 64. Sum of 11 is 6 out of 64, but we had that before. That's 3 out of 32. A sum of 12 is 5 out of 64. A sum of 4 is 4 out of 64, but that was 1/16. A sum of 14 is 3 out of 64. A sum of 15 is 2 out of 64, but that was 1/32. And then a sum of 16 is 1/64. Okay, and I would like you to give those probabilities or relative frequencies, give them as fractions in the table. And then for actually graphing the probability distribution here, it could be helpful. Well, actually, we may not need to. You may, or it could be helpful to get decimal approximations. However, you wouldn't necessarily need to. So to actually then graph this, you're graphing it as a bar graph. If you notice, like we see on the front, you should have spaces in between the bars. So don't make a histogram where you don't have spaces in between. There should be spaces in between the bars. I'm not sure with the grid I gave you. Maybe it does work if you like have this square as one and then you skip one. It might work actually if your first bar is this first graph. So if here we start with a sum of 2 and then we skip 1, sum of 3, and so on. So make sure there is a space in between each of your bars. And then I do need to label here so I know how high to make the bars. And what you're graphing is the probabilities. You're graphing the relative frequencies. So this is what I was saying. I might actually, well, actually, I don't want to do that. I'll label these as fractions. So I'll start, the very bottom line would be 0. And then this first line I'll label as 1/64th, and I'll just go up by 64ths. So label this as 1/64th, and then the next line would be 2/64ths, and I can go up. You could also put a scale to it and say these are all 64ths and just label it 1, 2, 3, 4, 5, and so on. So you'd have to choose, or rather along the bottom, those are that's your sample space, in this case the possible sums we had. The y-axis should be labeled, you are plotting or graphing the bars, the height of what their probability was. Okay, so then I go off of the table and I say a sum of 2. The height of that bar, that probability was 1/64th. So I draw a bar with a height of 1/64th. Okay, and then I continue that for all of them. So a sum of 3 had a height of 2/64ths, which was 1/32nd. 4 was 3/64ths. And so on. And the sum of 9, that was the highest probability. So you should see that's the highest bar when you're making your probability distribution. After the sum of 9, it starts to go back down. And as you're finishing that up, I'm just going to talk through the rest of this lesson here. So first of all, if you look at this distribution, based on the types of distributions we talked about yesterday, what type of distribution would you say this has? Symmetric, yes. Now, I do want to specify not every probability distribution is symmetric. So you will see probability distributions that do not look like this. It doesn't mean that it increases up until the middle possibility and then starts to decrease. That's not always the case. So don't get that in your mind that it has to be a symmetric distribution. It doesn't. Your tables do not always work out the way this one did, where you see similarities in these values here. So like I said, it's very important that when you're coming up with your sample space that you're actually listing out the possibilities. I know it takes time, but list them out so you know what the possibilities are, you know what the frequencies are. At the bottom, I just talked a little bit more about experimental probability distributions. For that, for this example, to come up with an experimental probability distribution, what I would have to have you do is I would say, okay, for 64 tries, I want you to actually do this. I want you to pick one card, put it back, pick another card, and then tally what sum you got. So all of your frequencies would be based on what you actually got. So it would look different than this probability distribution. What this is explaining at the bottom, you may have heard of the law of large numbers before. The law of large numbers states that if your sample size increases, the experimental and theoretical probabilities come out to be approximately the same. So, for example, if I only had you do this, say, 5 times, your experimental probability distribution is going to look way different versus if I had you do this, say, 100 times. It's going to look closer to what it should look like. So that's just some additional information at the bottom.